Let's look at question 3. Question 3 carries 10 marks. And question 3 reads, a simple regression model is to be built which predicts company profits based on the number of full-time employees in the company based on the above data. And the first thing that we need to do is build such a least square regression model. And then we'll give an interpretation of the model. Then we'll interpret the R value, or the coefficient of correlation. And then we'll interpret the R squared value, which is the coefficient of determination. And then we will have to predict the expected profit for a company that employs 25 people using the model that we've created. So in order to answer this, let's go to the raw data. Okay, and so this is the Excel file. There are two variables that are of interest here. It is the number employed and the company profit over 2 years. So what I like to do is copy these two variables to a new worksheet. So I'm going to create a new worksheet here. So maybe we can call this worksheet linear regression. Yeah, and I'll paste it right here. We'll have to copy it again. Okay, so we got the number employed, number of full-time staff employed, and the second variable of interest to answer this question is the company profit over 2 years. So we're going to copy that, put them away here, and we'll paste it beside the number employed. Okay. So you realize that the number employed is a count variable. Okay. So it is a quantitative variable. And then the company profits over 2 years is a continuous variable. It is also a quantitative variable. So now we are asked to use these two variables to develop a linear regression model. So before we build a linear regression model, what I like to do, and what I think you should do as well, is do a simple correlation analysis. And after the correlation analysis, we'll calculate a scatter plot of the company profits. Now, it is important that you identify that this is the dependent variable and the number of full-time employees, which is the independent variable. And from that, we'll get a better understanding of our data and the relationship between these two variables. So in order to do the correlation analysis in Excel, we go to Data. We'll click Data Analysis, and we're going to select Correlation. Okay, so for the input range, I'm going to select these two variables, all of them. Okay. There are 92 entries here, and we've grouped them by columns. Okay, the first row is the labels, and I'm going to put them in the same worksheet. I wanna so it's easy for me to see them. And I'm going to click OK. So here we have the correlation analysis output. Okay. Now you can see the correlation between company profits and number employed is 0.99. Okay. So this means that there is a strong, there is an almost perfect, I should say, positive correlation between the company profits over the 2 years and the full-time employees employed in this company. So just want to make that prominent, and put columns around. I don't know, it's something that I like to do. You don't have to do it if you don't want. So this is the correlation coefficient, which is denoted by either capital or small r. So I'm just going to put small r there, 0.998. Okay, I'm rounding it off to 3 decimal places. Now, after I do that, I really want to see the relationship using a scatter graph. So I'm going to do a scatter graph of this. And to do the scatter graph, we'll go to Insert. And then we'll come over to the graphs here, and we'll choose this one. Okay? This will be the scatter graph. Just right-click there, and we'll select our data. And for our data, we'll select all of this. The primary data here. Okay. Now, oh, it's giving them in line plots. Anyway, just switch. Just click switch here. Okay. So now we have the scatter plot. You can see this is almost a perfect correlation and line between the company profits in Kina in the y-axis and the number of employees in the x-axis. Okay, and we'll just click OK. Now, one thing that we can do is we can just click this plus sign on the right side of the graph here, and we'll add the trend line. Okay, so that's a trend line there, and then I like to put in the equation. Okay, so and then we click display r squared and click the display equation on the chart, and so we've got our two. So the scatter graph, gives us the regression model here, which is y is equals to 60,053x minus 10,507. That's the regression model. But we'll calculate this using the regression model analysis toolpack. But r squared here is 0.996 if we round it to the nearest 3 decimal places. Now, it's the square of the correlation coefficient. So it's 0.998 squared is actually 0.996. Now, this is the coefficient of determination. This is the coefficient that predicts future profits given a change in the number of employees. Okay? Okay. So with that being said, now let's go over and do our, I'm not going to edit this table, and you can do that if you want to, but I'm not interested in that. I'll just go straight and do the least regression model. So in order to do the least regression model, least square regression model, we'll go to data, we'll click data analysis, and then we'll click regression. Okay, so input y, this is the dependent variable, and the dependent variable is actually company profits. So we'll select the company profits into that cell there. Okay, and then it says input x. X is the independent variable, and that is the number of employees. So we'll select the number of employees into that space there. Okay. Now we'll select labels. Okay. Now you can select all this if you want to, residuals and standard residuals and all that, but I'm not going to do that. I'm going to click confidence interval because I want that to come out. Okay. And then I'm going to click output, and I want it to be in the same worksheet. Right. I want it to be in the same worksheet, so I'll put it right here. And I'm going to click OK. And there we have it. That is the output of the least. I'm just gonna fix this up so you can see, so we can all see clearly. Okay. This the upper 95% and the lower 95%. There's a repetition here, so we'll remove this one. The one to the right. Okay. So for the so this is the output. Okay. And you can you can see that we've got three tables here. That's the regression statistics, the ANOVA table, and another table that gives us the coefficients, standard error, the t-statistics, the p-value, and the confidence interval, the 95% confidence interval. So let's interpret this, right? So, but to interpret this, we'll be answering question 2. So I think this is the answer to question 1. Okay, you can just fix this table up and put it into your answer. Now, if you see this, like there's this the sum of squares here for the ANOVA analysis, you can see at the end there's an e plus 15. Okay, if you see an e plus, it means that it is 15 decimal places. The actual figure is 15 decimal places to the right. Okay, now there's somewhere you can see there's e minus 108. Now this means that there's 108 decimal places to the left. So this number would be 0.108 zeros 225752. Okay, and that's a very, very small number. It's almost 0. Okay, so we can accept this as 0. So I'm just going to put 0. I'd like to put 6 zeros there, and then that's fine. Let me see, some 6 zeros. 2, 4, 5, 6. Okay, and that's enough. We have here we can see as well there's 108 zeros. So I also will put 6 zeros there. 0.1, 2, 3, 6. Okay. Okay. Now, and that's the answer to our first question. For the second question, it says, give an interpretation of the model. Now, I think you should also put the equation down here, or the actual model, which is y is equal to the gradient, okay? The gradient of the number employed, and the gradient is 60053. I'm just going to round it up to the nearest whole number, x, and then it will be, the intercept is minus 10557, and I'm going to round it off to the nearest number, so that would be 10578. And that would be my regression equation. Okay, let's go to question 2. So question 2 says, give an interpretation of the model. Okay, let me interpret this model now. So let's interpret the first table here, the regression statistics. Here there's a total of 92 observations. That's 92 companies that were included in the survey. The multiple R regression here, okay, is the correlation coefficient that was derived in our correlation analysis above. The R squared, which is 0.996, is the coefficient of determination. Okay? And the coefficient of determination determines how much of the data in your study can be explained by this regression model. Okay, so this means 0.996 means that 99.6% of the data observed can be explained by this regression model. Or another way to put it is that 99.6% of the variation in profits generated can be explained by variation in the number of full-time staffs employed. This also means that only 0.4% of the data observed cannot be explained by this regression model, and that's quite negligible. It's almost close to 1. So these are the two main variables that you want to interpret up here. I'm not going to do this. I don't think that's important. The adjusted R squared. I think the adjusted R squared is important in multivariate regression analysis, and I'll leave out the standard error. In the second table, we have the ANOVA table, and this shows the degree of freedom, the sum of squares, the mean squares, the F statistic, and the significance of the F statistic. And this is the p-value, all right? It's the p-value. Now you can see the F statistic is 20,922, and this is far, far greater than the critical F statistics, and thereby the probability value is much less than 0.05. So from this table, from the ANOVA table, we can conclude that we will reject a null hypothesis and accept the alternate hypothesis that there is a statistically significant relationship between the number of full-time employees and the profits generated by the company. Okay, try to use the appropriate terms. Now, in the third table, which is the most important, are the coefficient of the numbers of staff employed here, and the intercept, which is there's a minus here. Okay, so that would mean the intercept is below the 0 point. Okay, and we have the standard error, the t statistics, the probability value, and the 95% confidence interval. So we'll follow the simple linear regression equation. If you remember, it is y is equal to b naught. Okay, y is equal to b naught, that's the y-intercept, plus b1 x1. Okay, and b1 is the slope, b naught is the intercept, x is the x is the number of staff employed, and y is the profits generated. Okay, so the coefficient 60,053 of the relationship between the number of staffs employed and profits generated. So the intercept of minus 10.10577 indicates that negative 10,578 kina is the portion of the profits not explained by the number of full-time employees. But we know that negative 10,578 kina does not exist in reality, as no company can do contract work without any employees. And so this is used to predict profits generated in the equation. The coefficient of 60,053 indicates that the average profit generated increases by 60,053 for each additional staff employed. Okay, so that's what the intercept and the number of employed, the coefficient of the number of employed mean. The t statistic for the number of full-time staff employed. I'm just going to highlight this important data here. Okay, so the t statistic of 144.65 for the number of staff employed is high. It's much higher than the And the p-value associated with that t statistic is less than 0.05. Okay, and it's 0.00000. Like we said, it's 0.000 to 108 decimal places, but we can accept this. So this means that the relationship between the number of full-time employees and profits generated as described by the regression model here, okay, is statistically significant at a p-value of 0.00000 to 7 decimal places here that I've put. That is, that this relationship between the number of employees and profits generated is not due to chance. Okay? The 95% confidence interval of the slope B1 here, okay, is from 59,228 kina to 60,878 kina. And this is a very narrow interval and indicates the precision of the slope B1. So it indicates that the precision of the slope, this B1 here, is high. And it means that we are 95% confident that the true slope B1 lies between this specified interval. And the same can be said for the 95% confidence interval for the intercept BO, which is this one here. Okay? So, if we combine all these results together, I will interpret it as follows. The linear regression model predicts the profit generated by the number of full-time employees. And this model shows that profits generated can be explained to 99.6%. This is the coefficient of determination. So this profits generated can be explained by 99.6% by the number of full-time employees, and this was statistically significant at a p-value of 0.00000. This is a statistically significant, almost perfect prediction trend that profits generated is determined by the number of employees as given in the regression equation here. Okay? And if we are to put it in words, we will do profits generated is equal to in PNG kina is equal to actually x minus 10,578. Okay, where x is equal to the number of employees. Okay, and that's how we put it. Okay, but look, this is from this data. In the real world, any outcome is a determinant of a multiplicity of independent variables, and so a multivariate regression analysis will give an actual scenario of what the determinants of profit generation in these companies are, while we are adjusting for confounding and mediation effects. The third part of question 3 is to interpret the R value, or the coefficient of correlation, and this is it. The coefficient of correlation is 0.998 to 3 decimal places. Let me just put this to 3 decimal places. Okay. In fact, I'll put all of this to 3 decimal places. Okay. So how do we interpret the coefficient of correlation? We've calculated it here as well, and here during the in the correlation analysis there. I'll put it in 3 decimal places. Okay. So the correlation coefficient indicates the strength of the linear relationship between the 2 different variables, x and y, that is the dependent and the independent variable. In our case, the number of employees is the independent variable, and the profits generated is the dependent variable. So usually it is a Pearson's correlation coefficient. Okay, so our Pearson's correlation coefficient is R is equal to 0.998. This indicates an almost perfect positive linear relationship between the number of full-time employees and the profits generated in our company of 92 companies that were surveyed. That means that the profits generated by the company in our sample can be explained almost completely by the number of full-time employees and in a perfect positive linear relationship. So that's the interpretation of the coefficient of correlation. What is the interpretation of the R squared, or the coefficient of determination? And the coefficient of determination is a statistical measurement that examines how differences in one variable, this one here, can be explained by the differences in a second variable when predicting the outcome of a given extent. So you can see almost immediately from this that the coefficient of correlation relates to the data that we collected, and the coefficient of determination is used to make prediction of the outcome given a change in the independent variable. So our coefficient of determination is 0.996. This means that 99.6% of the data observed in our analysis here can be explained by this regression model. Okay? That's one way. Another way of explaining it, which I think is much more vivid, is that 99.6% of the variation in profits generated can be explained by the variation in the number of full-time staffs employed. So in other words, differences in the number of employed staffs explain almost all the differences to 99.6% in the profits generated. So 99.6% of the profits generated can be predicted by the number of full-time staff employed according to the equation here that we've calculated. Okay? Where profits generated is equals to 60,053 x minus 10,578, where x is the number of employees. And so that will be an explanation of the coefficient of determination. The final part of question 3 is that, let's see question 3, the final part. How well does the expected profit of a company that employs 25 full-time employees? Okay. So according to this equation here, let me analyze this equation. So according to this equation, profits generated, we are going to use it to calculate the profits given that a company employs 25 full-time employees. So this would be profits generated is equal to 53 times, right? Excel recognizes asterisks as the multiplication sign, times X, which is the number of employees, and our question says we've employed 25 new employees. Okay, we'll put a bracket around that. Okay, put a bracket around that as well. And then minus 10,578, which is the intercept. 78. Okay. That will give us $1,490,747 kina. I'm just going to change this to kina. Okay. So if we employ 25 full-time employees, we can predict the profit to somewhere around 1,490,747 kina. Now, if we do decide to put in the confidence interval, which is this, now you can use this value to calculate the confidence interval. And I've already done that for you. And I'm going to put the confidence interval here. Okay, just beside that. This is the 95% confidence interval. Okay. Let's see that. Okay. So this is the answer to the last part of question number 3. It is asking us to predict the profit generated given we employ 25 new staff, and the predicted profit is this here with the 95% confidence interval of 1,378,379 kina to 1,603,116 kina. So this means that we are 95% confident that the true profit generated, that the value of the true profit generated, given that we employ 25 new staff, will be somewhere in between this specified interval. But the one that we've calculated from this is this figure here. Okay? I hope this helps.